Hi everyone, in this video we will learn how to build a model for constant or uniform acceleration, and we'll use this model to solve an example problem. Let's get right to it. This one says, a speedboat traveling at a constant velocity of 20 meters per second passes a police boat at rest. The police boat decides that this is much too fast and starts his boat 8 seconds after the speedboat passes. The police boat accelerates 2.3 meters per second squared, at 2.3 meters per second squared for 10 seconds, then travels at a constant velocity. When and where does the cop catch the speedboat? Okay, so this one looks complicated. There's many things happening, right? In fact, we have two objects of interest in the same problem. Normally it's just one. We have now a speedboat, which I will use green highlighter for. And then we have a police boat, right? Now, speedboat, police boat, they kind of sound similar, and sometimes due to my Hispanic accent, they might sound identical. Therefore, whenever I refer to the speedboat, I'll just say boat, and then for the police boat, I'll say police, okay? All right. Now, normally we would want to start with our graphs, right? And we can definitely do that. Although we'll see, maybe we need a little bit more information. But let's start with the graphs, right? And I think you guys can see, at least for the boat, that one's easy, right? Because he's going to constant velocity. We have no information where it says, oh, the initial position is this or that. Therefore, we get to pick, right? And my suggestion, what we should do is say, well, we'll consider the time where the police sees the boat to be time 0 and position 0, or initial position and time, right? So the moment where the police sees the boat, that is time 0 and initial position. So everything's 0. That way the mathematics will be easier, right? So let's start with our graph. Let's start with the position time. So we now have position in meters. Yeah, so I'll go over here. Man, let's try that one more time. Yeah, just pretend it's straight, guys. Just pretend it's straight, okay? There you go, and there you go. Now, we do have information about time, right? And if you think about it, let's say we call this 8 seconds, right? Because there's 8 seconds. And as we call this one 18 seconds. That could help us, but still we don't know what's happening here on the vertical axis, on the position, right, axis. So we really can't build a graph. I mean, we can't just say, all right, it's constant velocity, right? Therefore, the guy will just go like that. The boat. And that's fine. But we really want to be able to use this model to solve the problem. That's why I recommend, let's start with the equations first, and then we'll get our graph, right? And the graph will just confirm our findings. So now what I want to do is I want to highlight everything that's given for the boat. So we have the boat traveling at a constant velocity of 20 meters per second. Then we have time is 8 seconds, and then 10 seconds. Now, something that I want to share with you guys, time is the same for both objects, right? Which is to say, although we can say, well, 8 seconds corresponds to this to this part of the trip, 18 seconds to this other part of the trip. There's really no exclusive time for the boat and exclusive time for the police, right? That's why I will highlight those in yellow, because that is for both, right? So 8 seconds and then 10 seconds. But we'll give meaning to those later. Now, let's highlight the question, right? Because that applies for both. When and where is he going to get caught? That means, so when, we're talking about time. And where, we're talking about position or location, right? So we need to find some position and some time. Okay, let's write down, well, now let's highlight whatever we have given for the police, right? Now, the police was at rest. Then he decides this is much too fast, right? Now, those 8 seconds, you can think of those 8 seconds as the reaction time, right? So maybe he thought about it for, a few seconds, literally 8 seconds, and said, you know what? No, I'm going to give this guy a ticket. So those 8 seconds, although they're part of the problem, during those 8 seconds, the police is not doing anything, okay? Now we know he accelerates at 2.3 meters per second squared. Now those 10 seconds will help us for the police, but still they apply for both, okay? Then the police travels at a constant velocity. So if we pick the reference frame of the police, we have the police at rest when he decides if he's gonna get the boat or not, like catch him. Then we have when he's accelerating. Then finally we have when he's going at constant velocity. So it's like 3 parts. Now let's write down the given for the boat, right? So I'm gonna say given, and that's gonna be for the boat. And we have, well, a constant velocity. When the velocity is constant, we can just call it v, right? Which is 20 meters per second. And then we have 2 different times, right? I said we should try to use the reference frame of the police boat. So for the 8 seconds we have, yeah, that's okay, right? Like he's moving. However, we want to know where he was at 18 seconds in. Why do we want to know 18 seconds? Well, for the first 8 seconds, he just went at constant velocity, but the police did nothing. Now, 10 seconds after, right, so a total of 18, that's when the police had accelerated and then started going at constant velocity. So we want to see what is the total distance he traveled, right, the change in position for those 18 seconds. So for the time, I'll pick 18 seconds. Then we want to know his position, so his displacement, that is delta x, we don't know. Let me do a line over here. What equation can we use to find displacement? Well, this is a kinematics problem, so I have the kinematic equations over here. We have uniform acceleration. Now we can't use that one because he's going at constant velocity, so there you go, there's no acceleration. We can't use this velocity one because this one has acceleration too, and we said that when velocity is constant, there's no acceleration. This one has acceleration, so nope. We can use one of the bonus ones, right? I said that this one works only when you have uniform acceleration. And at least for the boat, we don't have any. We have to pick this one. And it works, right? You'll see. So now we have x is equal to x naught plus vt. Although it doesn't look like we have displacement, we can get displacement, right? All we do is we know that displacement equals x minus x naught, final position minus initial position. Therefore, we move this one to the left, right? I'm going to erase this. Basically, we would just subtract x naught from both sides. I'm going to erase it because I don't have that much space, right? And then we'll get delta x is equal to vt. Now, furthermore, we said that the initial position was 0, right? That's how we set it up. So this one would still cancel, and we end up with the same thing, right? Uh-oh, that was my bad. Sorry. So now let's substitute. We have delta x would be velocity, 20 meters per second, multiplied by the time, which is 18 seconds. 20 times 18, that is 360 meters, right? So from the point when he was spotted by the police, the police is 360 meters away from that original point, from that starting point, okay? And then don't forget, I'm going to just write down over here, this displacement corresponds, or is at, better said, at 18 seconds. All right. So now, let's see what we have for the police, right? So given police, we know he was at rest, so that means his initial velocity is 0 meters per second. Then, we'll deal with the time later, right? Then he accelerated at a rate of 2.3 meters per second squared. And he accelerated for 10 seconds. So his time is 10 seconds. Now, something to note over here. These 10 seconds, they correspond to the boat's (18 seconds). Okay? Because this 10 seconds is 8 seconds after the boat had passed in front of him. And now he's going to constant velocity, right? So, I mean, after that he went to constant velocity, so we don't know what that is, right? What is the velocity after he was done accelerating? And based on what we have, if we go back to the kinematics, well, we can use this one over here, right? Because we have, well, this is 0, but still there. We want this one, we have acceleration, and we do have time. So let's see. Equation, okay. We have velocity final equals velocity initial plus acceleration multiplied by time. Well, velocity initial is 0, so that this cancels. So this one simplifies to just 18. We substitute velocity equals acceleration, which is 2.3 meters per second squared, multiplied by 10 seconds. So his velocity is 23 meters per second. So when the police was going at constant velocity here, this means 23 meters per second, okay? Now, from this information, we know he will catch the boat because the boat was going at all times, right? Constant velocity of 20. After he's done accelerating, he's going at 23, so eventually the police will catch the boat. Now, what we want to see is from the starting position, right? From x equals x, from x naught, starting position, where is the police boat, right? So after the 10 seconds passed, where is he? What is his position? So for that, now in this one, I'm going to say the initial position is 0, right? X naught equals to 0 meters. We want to know what is his final position, right? Now we have x and x naught. If we go back to the kinematic equations, well, the one we have to use is, I mean, I guess we could use this one, right? But we have time, so, my bad. This one's good, right? We can use this one. It'll be a little bit easier. Let's use that one, okay? Because look, this one will give us x, that's what we're looking for. This is 0, initial velocity is 0, so this will simplify rather nicely. So now I'm going to use a different color pen just to show a different process, right? Still police, but I want to show a different process. You know, a darker blue, yeah, darker blue is better. So we have x is equal to x naught plus v naught t plus 1/2 a t squared. Initial position is 0, velocity initial is 0. So regardless of time being 10, 0 times 10 is 0. Therefore, our equation simplifies to 1/2 a t squared. Now we just substitute. X is equal to 1/2 A, which is 2.3 meters per second squared, times the time, which is 10 seconds, and then we squared. Let me try that S again. Because S is a difficult letter for me to write, okay? Now, let me use decimals. There's decimals. To see what that number is, right? So don't forget parentheses are your best friends. So 1/2, 2.3 times 10 squared, that's 100. And we have 115. So here, the police is 150 meters from the moment or from the point where he saw the boat, right, speeding. So there you go. That's that. So now we can say the boat's final position equals 115 meters. All right. We have good information, right? We have good information. Now, let's try to draw our motion graphs. Let's start with the position time. Okay. So this is X. This will be T. And the time frames we have is, well, it's 8 seconds. And let's say over here is 18. Actually, I'm going to need to extend this one, right? Well, I mean, no, that's fine. That's fine. And if we go back, the two displacement we have the final position of the boat, which is 360. And then we have the position for the police, which is 115, okay? So let's add them up over here. I'm going to say this is 115. Don't forget it's X in meters, time in seconds. Let's try that S again. And what was that other one? 360. So maybe here, right? Not to scale, but you guys get what I'm trying to say. So we know that the boat at 18 seconds, he was here, right? And there's just a straight line because he's going at constant velocity. There you go. Now the police, however, he accelerated, right? Now for the first 8 seconds, the police was not doing anything, right? So that means from 0 to 8, he is like that, at 0. Then he accelerates, and he gets to this point at 18, right? Now we know that acceleration has to show a curve, so something like that, right? And then the police will go at constant velocity. So he will just go from here, kind of like this, right? And the boat will just keep going at the same rate. Now notice that if I keep extending, right, there'll be a point where they meet. So here, right, this is the point of interest. So we want to know here, what is the time, right? This is the time. Let's call it, just time, right? Time is time for both, so just time. I know what's this one. And we want to know this location, right? This position. Now, I don't have enough space on my graph, but we can call this the location or position when he gets a ticket, right? So XT. That's what we want to know. We want to know what is the position where he gets caught and what is the time when that happens. Okay, so that's how the position time graph would look. Now let's try the velocity time. I think that one's going to be easy too. So we have, there you go. There you go. This is velocity, meters per second. This is time in seconds. And the two velocities we have are 20 20 for the police, I mean for the boat, and then 23 for the police, right? So we'll say maybe this is 20 and this is 23, right? Now the boat was going at constant speed at all times. So this is just, oh wait, let me add the times, right? So let's say 8 seconds is here, and this is 18 seconds. So then the boat was just going at 20, right? It just was going at 20. Now, the police at first, for the first 8 seconds, was not moving, so he's at 0. And then he gets to 23 at the 18-second mark, so 10 seconds later. So he'll be at this point. Right now, this is constant uniform acceleration. Therefore, it goes like that. Oh, let me try that again. That was. There you go. That's better. Now, I know they intersect here, but this is just velocity, right? So at some point, the police had a velocity of 20 meters per second because he eventually got to 23 meters per second. So don't think that's where they meet, okay? This is just showing that the police ended up going faster than the boat, right? The police ended up going faster than the boat. Because at this point, after 23, right, now the police will just go like that, right? A constant velocity. And so will the boat. So there you go. Now the acceleration one. That one's super simple, I think. So we have acceleration in meters per second squared. And this is time in seconds. Let's say this is 2, right? Now the boat was not accelerating, constant velocity, so here we go. 0 at all times. And let me add the time, right? So this is 8 seconds, and this is 18 seconds. So the police, for the first 8 seconds, was not doing anything, so at rest. However, after that, he accelerated for 10 seconds at a rate of 2.3, so just a little above 3. So this is the way it would look, right? Because he accelerated for 10 seconds. This part here, guys, this part here shows the acceleration of 2.3 meters per second squared for 10 seconds, right? From 8 to 18 is 10 seconds. Then after that, he goes to constant velocity. So back to 0. So there we have our motion graphs. And of course, the one we want to use to solve it is this one, right? Position time graph. Because we need to find a position and then a time. Okay. Now, let me use my other paper. And let's see, we have to find, right? We have to find the position where he gets the ticket. And then I guess we call it T final, right? Just final time, like the final time, TF. Okay, what do we know? Now, all this was the setup, guys. All this was the setup. Now we're going to focus on the third part, right? When he is going to constant velocity, when the police is going to constant velocity and is going after the boat, okay? That is our starting point, okay? Now we can no longer call it 0 because we know that's 18 seconds in, right? At 18 seconds, the boat is at 360 meters and the cop is at 115 meters. 115. The police is going at 20 meters per second. And the police is going at 23 meters per second. I don't know if I said the police, right? The boat is going at 20 meters per second and the police is going at 23. So that's going to be our initial position and time and velocities. Now for the boat, everything having to do with the boat, I'll use the a B, right? So initial position of the boat, x naught b, equals 360 meters. The initial velocity of the boat equals 20 meters per second. Well, in this case, I can call it velocity, right? Just velocity because it's constant. So let me do that. That'll make it a little bit more legible. There you go. The velocity of the boat is 20 meters per second. And that is, yeah, that's all we have, right? We want to know the time final is the same for both. So I'll use black, time final. We don't know. And X, when he gets a ticket, we don't know. Black means it's the same for both. Now, for the police, his initial position, so X naught P, I'll use P for police, equals 115 meters. And his velocity of the police is 23 meters per second. Now, they're both going to constant velocity, so that's why I'm not using V naught or V final, just that, okay? And look what they share. They share time final, right? Because it's gonna be the same for both. And XT, so that's the location where he gets a ticket. Now, based on the information we have, right? X naught, V, T, and X final, X initial and X final for both. What is the kinematic equation we can use? Well, not this one, they're not accelerating. Not this one, they're not accelerating. Not this one, they're not accelerating. So this one, right? That's the one we want. Let's see, right? So then, we can say, for the boat, final, so this is the final, right? The final is the same. So, xt is equal to initial position, that's for the boat, right? Plus the velocity of the boat multiplied by time. Time is the same for both. Let me move this a little bit, okay? There you go. Now, for the police, we have, well, let me move it a little bit more. Just a little bit more, right? That's the boat. Now, for the police, we have location where he gives a ticket. Now, this is location where he gets a ticket. And this is location where he gives or writes a ticket. All right. Equals the initial position of the police plus the velocity of the police multiplied by time. Now, what we should do is solve for time, right? So these two equations are both equal to x sub t. So we can set them up equal to each other, right? Now I'm going to use black from now on. So I can say x naught boat plus velocity boat. That's equal to x naught police plus velocity. Oh wait, I made a mistake. I missed the time. Forgot about the time. T. That's what we're solving for. So x naught police plus velocity of the police multiplied by time. So let's solve for t, right? There's two of them, so we got to do some algebra. Not complicated. So the first thing I'm going to do is I'm going to move the initial position of the police to the left, right? Now, although both of them are x naught, they have different subscripts, so I cannot simplify these two. I cannot simplify them. So then this cancels. So I have x naught boat minus x naught police plus velocity of the boat t equals velocity of the police t. Okay, but let me move this so I have a little bit more space. And then this is what we do. We move this velocity to the left. Move this velocity to the left. The police, right? VP t. Now, I cannot split t from velocity of the police yet because that would make everything very, very complicated. Wait, no, what am I doing? My bad, Man, I don't know why I got distracted. So, this is the one I have to move, guys. Velocity of the boat, t. There you go. Right, because I want to have both t's, or time, on the same side. This cancels. So now I'll have x naught boat minus x naught p equals v sub p t minus v sub b, as in Bravo, t. Now I have both times, or t's, on the same side, and I can, yes, you guessed it, factor. Okay, I can factor. Well, that's cool. I didn't know I could do that. Now let's factor out this one. It'll read like this: x naught v minus x naught p is equal to t velocity p minus velocity b. Now we're one step away. We just divide by the two velocities. Wait. Two velocities in the parentheses. This cancels. Vp minus v Bravo. And our time, well, let me make this a little bit smaller so I can write it on the side, because I'm running out of space. Can I do it smaller? Can I make it smaller? No, I can't. Sorry, I'm too used to OneNote, guys. But I like this one too. So now time will be x naught boat minus x naught police divided by velocity police minus velocity boat. Let's substitute, right? That should give us a time. We have all that information. Time is equal to x naught boat, that is 360 meters, minus x naught police, 115 meters, divided by police velocity, that is 23 meters per second, minus 20 meters per second. Let's see what that is. Let's use decimals again. Right, don't forget parentheses are your best friends. So 360 minus 115 divided by 23 minus 20. So you have 81.67. It is important that we understand what this 81.67 seconds mean, okay? So this is 81.67 seconds after the 18 seconds had passed. Don't forget we had 8 seconds, which was the reaction time of the police, and we had an additional 10 seconds when the police was accelerating, okay? So this is 81.67 after. Sorry, 81.67 seconds after, okay? Let's write that down. So we have this time, right? I'll call it time 3, right? Because this is the third part we said. Time 3, third part. Time 3 equals 81.67 seconds. All right. So now if this let me change. There you go. 7 seconds. Now, if you think about it, is this time, so we'll call it T3, right? That's the time, right? No, that's not, my bad. So this is a total time, right? This will be T total. Let me change, yeah, or T final, let's call it T final. Yeah, T final, that's better, T final. Now, what we found truly was from here to here. This is T3. That's the 81.67. Remember, this is not to scale, okay? So now, to know what was the total time, right? The total time for this event, we just add them up, right? So let me go to the third page. The other page. There you go. And let's see. To find the total time, now the total time is for both. The final time, right? Time final equals the 8 seconds we had plus the 10 seconds we had plus the 81.67 seconds. Okay? Don't forget, this time it was just the boat moving. This time it was the police accelerating. And this one is kind of like the chase, right? We called it. So now we want to see when the boat will get caught. So we have to kind of think it in terms of the boat, right? Because this is the one getting caught. And that'll help us find where is it that he gets caught, okay? And we know the total time over here will be, well, we'll add it later, okay? I don't want to add it now. So you can everything combined. We'll use green, right? Because we want to know when the boat gets caught. So we know that the boat had a velocity constant of 20 meters per second. And then when we combine these three, that'll be the total time from the moment he was spotted by the police to the moment he gets pulled over, or whatever they do for boats. I don't know the dynamics there. So this time, let's use decimals. Yeah. I would flex with mental math, but I don't want to do that right now. I'm tired. So it'll be 18 plus 81.67. 99.67. Cool. 99.67. If you did that before me, because you're very good at mental math, that is good for you. I'm proud of you. 99.67 seconds. That'll be the total time, right? Or time final. And we want to know what is the total displacement, right? For the entire trip. We're finding this point, the xt, we called it, right? Xt. So I guess we can call it xt, because that's where we said we would call it. So xt, x ticket equals delta x. Alright. We can use kinematic equations. In this case, we actually use the same one. We use to find the position, right? We'll use this one over here. Because we know his starting position was 0. We're going to see when he gets caught. And now we know, well, we know his velocity is 20. And how much time passed till he got pulled over. So now we have x. Well, let me fix this, right? In this case, xt would be x minus x naught. And we know that x naught is 0. So therefore, xt is simply equal to x. So then, xt, which is equal to x, is equal to x naught plus vt. This cancels. So xt equals velocity multiplied by time. In this case, is the total time. We're time final, okay? So now we have xt equals velocity, 20 meters per second, times the final time, which is 99.67 seconds. Oops. Can I move that? Yeah, there you go. And xt is equal to, let's get decimals going. So I'll use 20 meters times my answer, because my answer is the time. 1,993.4 meters. There you go. That's the distance. So he'll travel almost 2 kilometers. That's like, what, like about 1.5 miles more or less till he gets caught. So 1993.4 meters. That's when he gets caught. Okay? And let's box the answer. That's where, and this is when. There you go, guys. That's how you build a model for uniform acceleration to solve problems. Now, the ones you'll do will not be as difficult, I promise. But now you know what to do, okay? Graphs, equations, graphs, and maybe more equations. That's it. Bye.